Hello and welcome to first lecture in chapter 21. The name of the chapter is Advanced Statistical Analysis. In this chapter, we are going to mainly study three topics. Topic A, exploring correlations and multi-collinearity in the data sets. Topic B, introduction to ANOVA and its application in Python. Now actually here introduction now will not be required because we have done ANOVA in much detail in chapter 19. So I can just modify this slightly. Revision of ANOVA. Just like in previous chapter, we revised the t-test and another was the chi-square test. Similarly, in this chapter, we are going to revise ANOVA. And topic C is some non-parametric statistical tests. Non-parametric tests are those which are useful when central limit theorem is not applicable. That is, some of the assumptions of the central limit theorem are violated, and at that time, parametric tests do not work. So, non-parametric tests are to be used. Now, at present, we are doing this first part, exploring correlations and multi-collinearity in the data sets. So, these are four subtopics in that. First, what is the importance of studying correlations in data science? Second, how to handle highly correlated features. Third, what is multi-collinearity? And fourth, we will use a data frame, that is the TIPS dataset, which is a built-in dataset that is available in the SNS library for demonstration about how to get correlation matrix heat map and one very important new topic, variance inflation factor VIF. Okay, so other things like correlation matrix heat map we have done here and there in a scattered manner, but this correlation is a so important topic that here everything regarding correlation we are doing in at one place for easy reference in future. So let us start with our topic A, exploring correlations and multi-collinearity in the data sets. So let us start with importance of correlations in the data science. Correlations are crucial because they indicate the strength and the direction of linear relationship between two variables. Now what is the meaning? So suppose here this is y, response variable, and x, that is feature. And if y and x are related, say in this manner, then you will say that as x increases, y also increases. This type of correlation is called positive correlation, right? Plus sign I am writing. But other type of correlation is also possible, maybe this way. So here what is happening, as x increases, y decreases. So this type of correlation is called negative correlation. So direction is of correlation that is decided by plus and minus sign. So here if y and x have a correlation of plus 0.6, so in that case you will say that as y increases, x also increases. But if the correlation between y and x is say minus 0.45, numbers I am just writing randomly, but the sign at present we are talking about. So then at that time we will say that as x increases, y decreases. So that is about direction in that word. And strength of correlation. Now for the strength of correlation, suppose I take again the example of one response variable y and one feature x. But on this axis, instead of just one feature, I am writing two different features. So one is suppose x1 black colored and another is suppose this x2 which is green colored. Okay, and I plot the graph of y versus x1 and y versus x2 both on the same graph paper, and suppose y versus x1 graph is like this, black colored graph for black colored variables y versus x1, right? And suppose y versus x2 graph is like this. Now here both are having positive correlation, right? Because as x1 increases, y increases, and as x2 increases, then also y increases. But here the increase in the y with this green colored graph is very steep. So we say that this is strongly correlated. So response variable y is strongly correlated with x2 while it is weakly correlated with x1. And how you will know about that strong and weak correlation? Then here the correlation coefficient would be say maybe 3. So a pretty high absolute value. While here the correlation coefficient will be say 0.31. So that is showing that this is a weak correlation. Both are positive correlation. This is also positive and this is also positive. But this is strongly positive correlation. This is weakly positive correlation. So correlations are important because they indicate the strength and the direction of linear relationship. So this is very important. I have explained two keywords, strength and the direction. And the third keyword is this linear relationship, because we mostly find Pearson correlation or other is called Spearman correlation. But they have one major limitation, that they are correlation coefficients for linearly varying correlations, like this kind of case. So that means if I have this kind of case, like maybe this, y and x are like this, and the variation between them is this way, this way, then such a correlation between y and x that cannot be perfectly measured by Pearson or Spearman correlation. That does not mean that correlation cannot be defined for this. There are other correlations, but we rarely use them in the data science unless you reach some advanced things in the data science. At that time, there are other correlation coefficients which we use. Okay, so three keywords are: correlations define the strength, direction of linear relationship between two variables. So understanding correlation will help in understanding relationship between the two variable or relationship between feature variable and y and x. Now this may not be always y and x only. It can be relationship between x1 and x2 also. So suppose this is one feature, say x1, which I am plotting on this x1 axis, x-axis, and this is another feature, say x2, which I am plotting on this axis. And suppose I find correlation between them, and I find that it is a linear and very steep curve, and I get correlation coefficient to be 0.95. So I would say that at that time my two features are around 95% correlated, or that means that in common language you can say that if I just keep any one feature out of these two, then if I suppose keep only x1 and remove this other feature, feature means a column, okay, so if I remove this column containing x2, that is that independent variable, then in that case also 95% of the information which could have been given by x2 is already captured by x1, so I am more or less on a safe zone. But if x1 and x2 they are connected in this manner, maybe this way, like this, now the correlation between them is very weak, so it may be say plus 0.1 only. And now in that case what is happening is that I cannot remove any one out of x1 and x2, because if I remove say x2 and keep only x1, but x1 can capture all its own information, 100% of its own information, but it can capture only 10% of the information which is provided by other independent variables. So this correlation study also helps in deciding which pair of independent variables are such that you can remove one of them without much loss of information, and which pair of independent variables are such that you cannot remove one of them without loss of information. And we have seen earlier that why we try to remove this feature variable, because if there are 20 features and you make a model, then such a model is called highly complex model or high parsimony, and therefore such a model is likely to overfit. But if you can find that two features are highly correlated 0.95, then keep only one and remove the other one. Similarly, other two are highly correlated 0.98, then again keep only one and remove other one. And from 20 features, many times it would be possible to make a model of only 10 features. So that simple model will be more generalizable and that will have less overfitting, right? So identifying relation which can be used for feature engineering, that is one importance of correlation, and avoiding redundant feature which improves the model efficiency and interpretability. For example, in one case we have done earlier, that was this case about the crop yield. Now, this kind of case we had done in chapter 19, right? That crop yield depends upon percentage cover and day length and average soil moisture. Now, these features, average max temperature, average minimum temperature, average air temperature. But actually, the three features here are redundant, because if you see, they have 99, 98 or that kind of correlation with each other. So, we decided that we will keep only one out of these three. So, let us say remove maximum temperature, minimum temperature and keep average air temperature only. But then we found a relation between average and air temperature and the response variable. So response variable is yield, and last line will give relation of response variable with various other. So average air temperature is here. Now that is also 0.06. So that means even average air temperature, the third one, two we already removed, maximum and minimum air temperature, and average air temperature which we kept, even that has so poor correlation with the final response variable that we can remove it. So three redundant variables are removed. Our model is simplified. Its chances of generalizing are improved, and still it will give relatively same accuracy, or maybe sometimes it will give higher accuracy also, and more importantly it will give higher interpretability to the model, right? Now, so first point about this correlation is this: what is the importance of correlation in the data science? Second is how to handle highly correlated features. So something I already told you in that example of crop yield, okay, this case, that how to handle correlated feature. So highly correlated feature can lead to issues like multi-collinearity in the regression models, and that can affect the precision of the estimation of model parameters. Model parameters means the accuracy, then R square, then precision, recall, etc. So this F1 score, so they are evaluated inaccurately if there is multi-collinearity present. That means if I don't remove this kind of features which are highly correlated. One another was also there, this 0.97 between Julian day and day length, right? So that feature also should be removed, because if I do not remove it, then the multi-collinearity will give metrics which are incorrect. Then what to do for handling that? You can do feature selection. Okay, now feature selection is removing or combining highly correlated predictors. So one is simply remove this, because for example here the relationship is so close, 99% and 98%, then I can always remove them. Okay, similarly here there is 97% inverse relationship between Julian day and day length, so even that also I can confidently remove. Sometimes the relationship is such that it is not that strong. For example, maybe correlation is, even this 83 is considered strong, but maybe this minus 0.52 here, or somewhere here there may be some correlation. Okay, even this 0.83 also. So there is 83% correlation between total radiation and time since last harvest. Okay, now if I don't want to remove them, because I see that they are correlated, but the correlation is not as strong as this 99% or 100% or maybe 97% like that. So I can try to make a new variable which is obtained by, say, multiplication of these two variables, total radiation multiplied by the time since last harvest, or by division of these two variables, or some other feature engineering. Okay, so in that way I am getting both benefits. When a new variable is created out of the ratio of these two variables which have 0.83 correlation, then I can drop the old two features, but still their complete information is captured in the new feature which you have added, which is the ratio of total radiation and time since last harvest. So you are not losing information, and still you are reducing the number of features. Okay, so that is called combining highly correlated predictors. So you not only always remove, if you find that the correlation is not convincingly high, then you can try to combine also. Then there is one other technique, which is called principal component analysis. That is very important technique, and we are going to study that in much detail. But principal component analysis is used to reduce the number of features, because in previous chapter I told you about only one response variable is one and only one feature, how to draw the graph of linear regression, and linear response variable is one and two features, and how to draw the graph of linear regression. Somewhat this kind of diagrams were there. Okay, so here this was one response variable and one feature, y and x. These were one response variable y and two features, x1 and x2. Here there is a line of best fit, while here there is a plane of best fit. Okay, so clearly for more than two features, if there would be there, then we cannot even draw the diagram, because the human eyes cannot visualize things more than 3D. In fact, we cannot visualize more than 2D also, but this kind of technique of drawing can be used to at least create a 3D like diagram on a paper. But what about if y depends upon x1, x2, x3, x4, x5, x6, x7, x8, total 8 features? Now at that time there is one technique which is called principal component analysis, and what that technique does is, if there are n features, then it will reduce them to only two features. So that means all these x1 to xn, where n is equal to 8 suppose, so x1 to x8, they will be reduced to only two features, like say x1 prime and x2 prime. Each of these features is called one principal component. So this is called one principal component, and this is called another principal component, right? And thereafter the equation becomes like this only, that is y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. That kind of equation it will be, because y is equal to beta 0 plus beta 1 x1 prime plus beta 2 x2 prime. That means all these 10 features or 8 features, they are replaced, and all these terms will also be replaced by just two terms in the equation. Then this type of analysis, that is called principal component analysis, and this is called first principal component, and this is called second principal component. So, but how to get such principal component? There are ready-made algorithms for that, but those algorithms internally use, we just call import PCA, and then we do PCA within just 2-3 lines of code. But internally those algorithms also use correlation, and they handle the multi-collinearity using principal component analysis. So two ways, in short, you just remember there are two ways of removing multi-collinearity. One is feature engineering, feature selection or feature combination engineering, and second is PCA, principal component analysis. There is another technique also which is called TSNE, and still another technique also for dimensionality reduction, and we are going to study all these techniques, not only PCA but that TSNE also, and many more different techniques for feature that is dimensionality reduction. So that will come in due course much later on, but we are going to study in much detail. So at that time, don't forget why we are doing it. We are doing it to reduce multi-collinearity. Okay, fine. Now what is multi-collinearity? Multi-collinearity occurs when two or more predictors are highly correlated. Now there is nothing to explain because that is what I have been explaining here. This is multi-collinearity. Point 0.6 or this is multi-collinearity. 0.83 is the correlation, high correlation. While this is also multi-collinearity but weak correlation is there. So maybe I can allow these features. But this is the correlation between response variable and feature variable. But if I have to plot correlation between two feature variables, then this kind of case is called example of multi-collinearity, while this kind of case is called not example of multi-collinearity, right? So if correlation between two features is very high, then that is called multi-collinearity. Correlation between two features is very weak, then it is not example of multi-collinearity. Because if two predictors means features, there is another word for features or another word for independent variables, that is the predictor word. Okay, and similarly for the dependent variable, the word is response variable or the target variable. So if there are two or more predictors or features highly correlated, then this redundancy can make the model's estimate highly sensitive to changes in the model. And now that means what? That if I just make a small change, maybe just one parameter's number of estimators. If you remember in random forest is a forest. Forest means it is nothing but multiple decision trees, right? So there is one parameter like number of estimators and estimators. So how many decision trees are present in your forest? That is given by this. Now if I have number of estimators 100 and next time I just keep everything else same, my data is same, my other parameters are also same, but next time I keep number of estimators 200. So forest is made bigger, 200 decision trees are present. Then just of this small change from 100 trees random forest to 200 tree random forest, that will change the model totally, model performance totally. So if that happens, that when changing one hyperparameter, model performance either greatly deteriorates or greatly improves, then you should not think that, oh, that second hyperparameter is better, okay, because it greatly improved the model performance. Because just by one hyperparameter, it might increase from 84 to 85%, that is fine. But if it improves from 84% to 94%, directly 10% jump, then be sure that there is multi-collinearity present in your data. Okay, so model becomes highly sensitive to changes in the model, and it can also be difficult to determine the effect of each predictor on the dependent variable because these two are highly correlated. So when you study their effect, x1 and x2, their effect on y, then the problem is that whatever effect on y is occurring, whether it is due to x1 or whether it is due to x2 or whether it is due to some interaction between x1 and x2, that we cannot decide, right? So that is why we first always try to eliminate multi-collinearity, and we try to ensure that whatever variables are remaining in the model, before we do that train test split and all those things, they have low correlation. So that means the features should not be such highly correlated like 0.95. They should be low correlated, say 0.1 maybe or 0.15. That is acceptable correlation. Okay. Now this is all. Yes. Why multi-correlation needs to be handled? Because one reason is this: it inflates the variance of coefficient estimates, leading to unstable prediction. So what is the meaning? Suppose your this model is y is equal to beta 0 plus, so beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Okay, let me add one more term also, plus beta 4 x4, right? Now that means solving this regression problem would be what? It is reduced to just finding the value of this coefficient. Okay, beta 0, beta 1, beta 2, beta 3 and beta 4. Now you can use any technique to find this coefficient, any algorithm, but before that, if your data set does not for your data set you have not yet removed such highly multi-collinearity 0.95 between two feature variables x1 and x2, and similarly suppose x2 and x3 also have 0.87, similarly x3 and x4 has 0.91, x1 and 3 have 0.95, x1 and 4 have 0.89, like that. But in short, various pairs of the features, they have high multi-collinearity. Then whatever estimates you get for this coefficient, they will be highly inflated estimates. That means they will be much more than what should be actually, because the basic assumption of this kind of model is that the features are independent of each other. So that means this feature x1 and this feature x2 and this feature x3 and this feature x4, they should be independent of each other. But if they are so highly correlated, 0.85, 0.95, 0.89, like that, so in that case you will get inflated values or much higher value of the coefficient than the values which you would get if the features were really independent, right? So that means variance of coefficient estimates will be inflated. So that is one thing, and complicates the interpretation of coefficient also, because coefficient, its interpretation we have seen, what is beta 1, then we had said that its interpretation as such is simple, that if I increase x1 by 1 unit, then whatever increase in y occurs, keeping everything else constant, that is called beta 1. So coefficient of x1 is nothing but change in dependent variable for unit increase in the independent variable when other things are constant. But the problem is if there is a high correlation, 0.95, 0.90, and so on. So in that case, when you change x1, do you think that the other thing will remain constant? No, because other are highly correlated, right? So in that case, how will you interpret what is exactly beta 1? Because x1 changes, then x2 will also change, and therefore y will change due to change in x1 and x2 both. In fact, x3 will also change and x4 will also change if all pairs are internally highly correlated. So then y will change due to changes in all four coefficients. Then what is the interpretation of beta 1? You can't say. What is the interpretation of beta 2? Similarly, you can't say. So you find it very difficult to interpret the coefficient, right? Now, in our next part, next part means in this lecture only, we are going to discuss this, or maybe next lecture, because I think already 31 minutes are gone. So we have done theoretical discussion. Now we will do the same discussion using a practical data set. And you know that SNS library has so many ready-made, high-quality, real-life data sets. So this tips data set we will take, which gives the tip which is given by in a restaurant at the time dinner or lunch, and on various days, Monday, Tuesday, up to maybe Thursday or Friday, that is weekdays and weekend maybe. Then by male or female clients, gender of the client, then by how tip varies based on the group of people who have come for lunch or dinner. So we want to study the effect of various factors on how much tip the customers give to the waiters in a restaurant. That is our well-known famous data set. So we will import that data set, load that data set from SNS library, and we'll continue our discussion, right? Okay. Now we will do that in the next second lecture of this 21st chapter. So see you in the second lecture. Thank you.